Okay, so we've reached this point in looking at the freezing point depression where we have this relationship between activity and the chemical potential, the difference in chemical potential. What we can do from here is take the derivative with respect to temperature. And so we're going to look at, on the right-hand side, we'll have d delta mu of fusion over T divided by R. dt, all of that divided by R, is equal to d natural log A1 dt. And these are partial derivatives, so everything else is held constant. And you may remember, if we want to look at the change in a Gibbs energy or a chemical potential as a function of temperature, that's given by the Gibbs-Helmholtz equation. And this partial derivative here is equal to let me make sure I have this right, it's equal to negative, I'm missing a negative sign here. I think I'm missing a negative sign here. Yeah, this should have a negative in front of it. But that partial derivative is equal to negative delta H over T squared. And this will be delta H of fusion. Molar. All this is molar values. Okay, and so what that lets us do is we can say that, so we're making a substitution with the Gibbs-Helmholtz equation, we can say that d natural log of A1 dt at constant pressure, etc., is equal to, our negative signs cancel, and we have is equal to delta H bar fusion over R T squared. Right, so we make this substitution using the Gibbs-Helmholtz equation to see how does this change with temperature, right? Because we're thinking about changing the temperature of the freezing point. And so we can then integrate this if we integrate over temperature, right? So we go from T fusion up to some arbitrary, whatever it goes, the T fusion star up to T fusion. So we integrate over, from the pure substance freezing point, right? So where this is the pure substance, where activity is equal to 1, up to, whatever our solution is. And we do the same on the right-hand side of the equation. This gives us a way to find the activity coefficient. So this will give us natural log of A1 minus natural log of the pure A1, which is equal to 1, so that term ends up being 0, is equal to this integral here. And so if we can measure the freezing point depression, we can use this relationship along with the enthalpy of fusion of our substance to find activity coefficients. So to find activities. This is another way we can do this. Oh, I forgot a dt here. Okay. So we can also, when you probably learned about freezing point depression the first time, you probably also saw that it's often represented in a much simpler equation, that the difference in our freezing point is equal to some constant, some freezing point constant, times the molality, m. So you may have learned about this in general chemistry. And we can get to this form from the integral that we just got by making some assumptions. So first assumption is that we can assume that delta H fusion is constant over the temperature range that we're considering, and usually this is a few degrees, so this is pretty good assumption. And we can assume that we have a sufficiently dilute solution such that natural log of A1 is approximately equal to negative x2, and we saw that, we've seen this approximation before. So if we make both of those approximations, we can then rewrite our integral as negative x2, that's the natural log A1 term, is equal to the enthalpy of fusion over R. Now those are both constants. Oh, no negative sign there. Times the integral of from T fusion star up to some arbitrary whatever our change in T fusion is, times 1 over T squared dt. So now this is something that we can solve. This is a pretty straightforward integral now. And we get that this is equal to delta H over R times 1 over T fusion star minus 1 over T-fusion, whatever the melting point changes to. Okay, and so now we have an expression, and that's, again, equal to negative x2. And we can rewrite this. Let me get my zoom back to the right value. Sorry about that. So now we can go ahead and rewrite x2 in terms of molality, because that's what we want to express everything in terms of. X2 in terms of molality is equal to molality divided by 1,000. We need to make the appropriate change to kilograms divided by the molecular weight of our solvent plus molality. And this is approximately equal to the molecular weight of our solvent times molality divided by our unit conversion here. And we can say that, okay, T-fusion is not going to change a lot from the pure substance, because we can rewrite this fraction up here as T-fusion minus T-fusion star divided by T-fusion times T-fusion star. And if we make these approximations, we can sort of simplify all this. This will give us Kf is equal to m1 over 1,000 grams per kilogram times R times T fusion star squared divided by delta H of fusion. This Kf will then, right, this is what, if we make all the substitutions, I'm skipping a lot of algebra here, but it comes from the assumptions that we have earlier. We can do the exact same thing for boiling point elevation. So if we look at the change in the temperature of vaporization, delta T vape is equal to temperature of vaporization minus the pure substance. And this, in this case, is an increase in the boiling temperature, is equal to this Kb value times the molality, and Kb looks very similar to Kf, where we have the molecular weight of the solvent divided by 1,000 to convert the units to kilograms times R T vaporization star squared divided by delta H of vaporization. Okay, so these are now quantitative expressions from the information about the particular solvents we're looking at that can tell us what these values of Kb and Kf are. And we can also use the data for the boiling point elevation or freezing point depression to find information out about our solvent. Particularly the enthalpy of fusion or the enthalpy of vaporization is directly related here. Okay, and so that is our discussion of the colligative properties of freezing point depression and boiling point elevation.